In this video, I want to talk about section 11.6. Okay, so 11.6 is going to involve two new tests. These are going to be our last tests for convergence and divergence, and they're called the ratio and the root tests, and they're actually very similar. Okay, so we'll talk about exactly what those tests are, how they work, and how they're helpful. They're actually very helpful and pretty robust. They work a lot of the time. But also, before we get into the ratio and the root tests, what I want to do is I want to describe that actually there's two types of convergence, and I want to talk about that. So divergent sums are still divergent. There's nothing that we're changing there. But it turns out that there's actually two types of convergent series, and I want to explain that. So there's what's called absolutely convergent. So absolutely convergent. And absolutely convergent series are ones where the sum of the absolute values converges. So we say that the series, let me write this a little better, the sum a sub n, say from 1 to, I don't know why I'm starting at 1, but this series is absolutely convergent. So this is called absolutely convergent if the sum of the absolute values converges. Okay, so that's absolute convergence. This is in contrast to what's called conditional convergence. So this sum a sub n, again, I'm just going to start at 1 for no good reason, but this sum is called conditionally convergent. So this is conditionally convergent if the series converges, but when you take the absolute values, you get a divergent series. Okay, so if the sum without absolute values converges, but the sum with the absolute values diverges, we call that conditional convergence. And I think it's worth talking about a few examples here. And so here, let's just talk about the alternating series. Let's say the alternating harmonic series, negative 1 to the n over n, as n goes from 1 to infinity. Okay, and this we said is, so this is the series 1 minus a half plus a third minus a fourth and so on. And if you take the absolute values, so if I look at the sum of the absolute values, this is going to be the sum from 1 to infinity of negative 1 to the n over n. And when you take the absolute value of n, that's just n is positive. The absolute value of negative 1 to the n is just 1. And so this is 1 over n. And so this diverges because it's a harmonic series. But the original series, negative 1 to the n over n, converges by the alternating series test. You know that the 1 over n terms are positive decreasing and tend to 0. And therefore, since negative 1 to the n over n converges, we say that this series converges conditionally. So this converges conditionally. Okay, so that converges conditionally. Again, the sum itself converges, but when you take absolute values, you get a divergent series because it's the harmonic series. Now, contrast this to what happens when we talk about something like negative 1 to the n over n squared as n goes from 1 to infinity. Here, the sum of the absolute values, if we have negative 1 to the n over n squared, the absolute values there are just going to be 1 over n squared, and that's a p series with p equals 2. It converges. And therefore, we call the original series, so this alternating p series with p equals 2, is absolutely convergent. We use the word absolutely because we're taking absolute values. Okay, so it converges in absolute values. Okay, so that's the difference. When you take absolute values and you get a divergent series, we call that conditionally convergent. If, again, if the original series converges. And if the original series converges and the sum of the absolute values converges, we call that absolutely convergent. Now, one thing that's true, think about how you feel about this, whether this seems obvious or not, but it turns out that every series that converges absolutely converges to begin with. So what I mean by that is that if you have an absolutely convergent series, those are convergent series, if that makes sense. There's a reason I'm saying that involves the ratio and the root test, which we'll kind of talk about that when we go through the ratio and the root test. But the ratio and the root test are going to be tied to these ideas of conditional and absolute convergence. So it turns out convergence involves, there's two types of convergence. There's absolute convergence and conditional convergence. Okay, so that's basically what I wanted to say about conditional and absolute convergence here. Notice that if I have a sum, so just to point this out, if I have 1 over n cubed, as n goes from 1 to infinity, this is a sum of positive terms. And therefore, when I take the absolute value, if I were to put in absolute value signs, I would just get back the original series. And so the only options that are going to happen here are if we get absolute convergence or divergence. There's no chance of it being conditionally convergent if we're adding positive terms, because conditional convergence happens when your original series converges, but the sum of the absolute values diverges. And that can't happen here because the sum of the original series and the sum of the absolute values is the same sum. So it can't be that one of them diverges and the other doesn't. So what that means for us is that this series has to either converge absolutely or diverge, and there's no conditional convergence. Okay, so this converges absolutely. We know it converges, therefore it has to converge absolutely. I can't spell, but you know this already, absolutely. Okay, so that's absolute, conditional, and divergence. It turns out, and this is a little bit strange, but I also want to add this to the end of this video, there's what's called Riemann's rearrangement theorem. So Riemann is the Riemann from Riemann sums, but this is Riemann's rearrangement theorem. And so what it says is consider a series, say A sub n, which converges conditionally. So think maybe of the alternating harmonic series. Think of something like that, something that converges conditionally. It turns out that the series can be rearranged. So the series can be rearranged to converge to any value. So the series can converge to any real number, okay? So to any value. This is a little bit strange. What this is saying is that if you take a conditionally convergent series, so for example, we have looked at the alternating harmonic series, -1 to the n over n as n goes from 1 to infinity, and this is 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, and so on. It turns out that the order that you add all these terms up will change what this converges to. And when you do it in just the straightforward order, this converges to the natural log of 2. And if you wanted to find a rearrangement that converges to, say, pi, you could do that. And what you would have to do is once you kind of understand why this works, this becomes a lot less mysterious. But basically, what conditional convergence means is that you have an alternating series, and if you drop the power of -1, you get 2 divergent series. And so basically what you can do is you can take all the positive terms and group them together, so 1/3, 1/5, 1/7, 1/9, And if you add all of those up, that's going to be an infinite series. That's basically a harmonic series or something like it. It's basically half of a harmonic series. And then if you look at the negative terms, that would be negative 1/2, negative 1/4, negative 1/6, negative 1/8. That's exactly negative 1/2 times a harmonic series. That's also going to diverge. And so what ends up happening is that you can take your positive terms and put them all in one pile. And that pile is going to have all the numbers that add up to infinity. And then you can take the negative terms and put those in another pile. And that pile is going to add up to negative infinity. And so you have two infinitely big piles to choose from. And if you want to figure out what's the rearrangement that you need in order to get to, say, pi, what you do is you take enough terms from the first pile so that you get above pi. So maybe you get to like 3.2 or something. And then you take enough terms in the second pile so that you get a little bit below pi. And then you take enough terms in the first series again so that you get back above pi, and so on. Okay, so that's kind of the idea. We may, in class, find a rearrangement of, say, the alternating harmonic series. That'll give us something else. But for now, I'm just going to leave that as it is. Okay, so kind of a slightly mysterious statement here, but it turns out it actually makes sense if you think about the fact that you really are kind of putting together two divergent series with the odd in the even terms. Okay, and so you can add all the positive terms until you get as big a number as you want, and then add a bunch of negative terms until you dip below that number, and so on. So you can kind of repeat that process so that you can have the series add up to whatever value you want. Okay, and so oddly, and this is very different than most of the arithmetic that we do or that we're kind of familiar with, it turns out that the order that you're adding things in when you're talking about infinite series, specifically conditionally convergent series, the order that you're adding in matters, and it'll change the value of the sum. Okay, so that's called Riemann's rearrangement theorem.